Good day everyone. A series of videos will be disseminated which will serve as your lecture 4. This lecture is prepared by yours truly, John Harold Aparici, and reviewed by my colleagues Calvin Pontawe, Mark Felipe, and Benedict Feliciano. In this lecture, we will discuss the following one by one. Let us start with a brief definition. Stoichiometry. Yes, it's pronounced that way, stoichiometry. It came from the two Greek words stoichion in English, element, and metron, which is measure. Formally, stoichiometry is defined as the study of the quantitative relationship between substances as they experience a physical or chemical change. Like what is listed in the coverage, we will start with mass and moles. Mass and moles are important concepts in stoichiometry because these quantities allow us to easily communicate what is going on to make sense of the changes. Mass is one of the fundamental units along with time, length, amount of substance, etc. It tells us how much matter is present in an object. Remember that mass is a defining characteristic of matter. Recall the simple definition: matter is anything that occupies space and has mass. Mass is mostly expressed as kilograms in the International System or SI, pounds or pound mass for the American Standard, and grams for the CGS system, centimeter grams second system. You can see here two pictures. The one on the left is a beam balance used to measure mass. On the other hand, a weighing scale, an instrument used to measure weight. Mass and weight are different, right? Weight is affected by gravity while the mass is not. Next, mole. Mole is invented by scientists to measure large quantities of very small entities, let's say atoms, molecules, ions, etc. Moles is extremely useful in calculations involving chemical reactions, which you will witness later as we discuss stoichiometry of chemical reactions. Mole, MOL, is the SI unit for the amount of substance. Like what I've mentioned, mole is used to quantify small entities. With that, we had the idea that 1 mole of X could be anything, is equal to 6.022 times 10 raised to 23, the Avogadro's number. Let's say we have here two blocks of metal, which are exactly 1 mole each. We have 1 mole copper and 1 mole silver. As you can see, they both have 6.022 times 10 raised to 23 atoms, which makes sense, right? 1 mole of anything is equivalent to the Avogadro's number. However, their masses are different. They have the same number of atoms, but each atom of silver is much heavier than that of copper. That explains their difference in mass, which tells us that it doesn't mean two things are composed of equal number of parts, they have the same mass. Molar mass is a pretty basic concept, but this is important, so let's talk about it for a second. Molar mass is the ratio between the mass and the number of moles of a given substance. Molar mass is the ratio between the mass and the number of moles of a given substance. This substance can be composed of one kind of atom only or a variety. If the substance that you are dealing with is composed of one kind of atom only, you just go straight to your periodic table, get its atomic weight divided by 1 mole, and that's it. Example: copper. Its atomic weight is 63.54 grams. Divided to 1 mole, we get 63.54 grams per mole. The same is true for silver. Its molar mass is 107.87 grams per mole. Now, if you're dealing with polyatomic molecules like methane, which has a formula CH4, you need to take the sum of all the constituent atoms. CH4 tells us that in a molecule of methane, there is an atom of carbon and 4 hydrogen atoms. The atomic weight of carbon is 12.01 grams. For hydrogen, it's 1.0079 grams. Times 4, since there are 4 hydrogen atoms. We add these values, we get 16.0416 grams divided by 1 mole, thus the molar mass of CH4 is 16.0416 grams per mole. Molar mass is helpful in conversions from mass to moles and vice versa. Speaking of conversion, we use the method dimensional analysis. Dimensional analysis is also known as factor label method or unit factor method. Here, we convert one unit into another by the use of conversion factors, like molar mass. The goal in dimensional analysis is to lay the ratios out in a way that the given unit cancels and the desired unit remains. Aside from grams to moles and moles to grams conversion, we can extend the process to convert from grams to atoms, moles to ions. This is applicable when the compound is ionic, and from one type of substance to another. This makes sense for calculations involving chemical or physical reactions. On to our first example, convert 12 grams of carbon dioxide into moles. Let us start by getting the molar mass. Carbon dioxide has a formula CO2, which tells us that there is one carbon atom and two oxygen atoms. The atomic weight of carbon is 12.01 grams. For oxygen, it's 16. We need to multiply that by 2 because there are two oxygen atoms in CO2. That gives us 32 grams. We add these values and divide it by 1 mole. Thus, the molar mass of CO2 is 44.01 grams per mole. So this problem is a conversion from grams to moles. So we will start with 12 grams of carbon dioxide. We will multiply that by the conversion factor. Again, in dimensional analysis, our goal is to lay the ratios out in a way that the given unit cancels. So we will purposefully write 44.01 grams on the denominator to cancel the grams unit and 1 mole on the numerator. Simplifying this, we get 0.2727 moles of carbon dioxide. Next, convert 12 grams of carbon dioxide into oxygen atoms. Like what I have said, we can extend the process to convert from grams to atoms. This kind of conversion is stepwise. This is the solution from the previous example. We will just extend this to convert from moles to atoms. We need to convert first the moles of carbon dioxide to moles of oxygen. In a mole of CO2, there are 2 moles of oxygen. Basically, just look at the subscript. In a mole of carbon dioxide, there is 1 mole of carbon and there are 2 moles of oxygen. So here we will be able to cancel the moles of CO2. We then multiply the conversion factor 1 mole X or 1 mole oxygen equivalent to the Avogadro's number or 6.022 times 10 raised to 23 atoms of oxygen. So the moles of oxygen will cancel. The unit now is atoms of oxygen. We simplify this, we get 3.2840 times 10 raised to 23 atoms of oxygen. Convert 0.2727 moles carbon dioxide into grams. 0.2727 moles carbon dioxide is the amount that we got from the first example. Basically, we're just doing the opposite here. So we expect 12 grams as the answer. Again, this is the molar mass. This conversion is an example of moles to grams conversion. We start with the number of moles, 0.2727 moles of carbon dioxide. We multiply the molar mass. In this case, we will place 1 mole on the denominator to cancel the moles unit. So 44.01 grams is on the numerator. We simplify this, we get 12 grams, so the answer is correct. Lastly, convert 0.5 moles of calcium hydroxide into hydroxide ions. The molar mass of calcium hydroxide is 57.089 grams per mole. This is an example of moles to ions conversion. It is possible because calcium hydroxide is an ionic compound. 0.5 moles of calcium hydroxide times the conversion factor, This is from the fact that calcium hydroxide is composed of calcium 2 plus ions and hydroxide ions. Now, from the formula, we can infer that 1 mole of calcium hydroxide contains 1 mole of calcium 2 plus ions and 2 moles of hydroxide ions. Now, the moles of calcium hydroxide unit cancels. We are left with moles of hydroxide ions, but we are looking for the number of hydroxide ions. So we multiply this by the conversion factor. 1 mole of hydroxide ions equivalent to 6.022 times 10 raised to 23 hydroxide ions. Moles of hydroxide ions unit will cancel. We are left with the desired unit. We simplify this, we get 6.022 times 10 raised to 23 hydroxide ions.